Hi, welcome back. Today we're going to talk about how we can integrate using substitution. We have been discussing how to integrate using the inverse of the derivative rules. For example, in our power rule, if we have the derivative x to the n, we know that becomes x to the n minus 1. But if we integrate x to the n, don't forget your differential, we add to the power and we divide. And we talked, and don't forget your constant of integration. So we've been talking about how to take the antiderivative using the inverse of our derivative rules. We even talked about our trigs and like sine and cosine. However, those inverse rules won't work on a problem like this one, the integral and the antiderivative of x squared plus 1 to the fifth times 2x, don't forget dx. Unless we decide we want to expand this all the way out, which most of the case, most people are like, oh no, I don't want to do that. So today's lesson is how do we integrate a problem like this one? So to do this, we are going to look at two previous skills. One is U substitution, and two is the chain rule from derivatives. Remember chain rule? We took the derivative of the outside function and we multiply that by the derivative of the inside function. And if you kind of look over here, we kind of see, look at this 2x. It kind of looks like it might be the derivative of the inside of the other one. Hint, hint. So, to begin, back in pre-cal, when you first learn how to factor something like sine squared plus 3 sine x plus 2, your teacher probably started off by saying, let u equal the sine of x. And then you would rewrite this as u squared plus 3u plus 2. Even though this looks really difficult to factor, this one was not. We could write this then as u plus 2, u plus 1, and you just put your u back in, so therefore we would get sine x plus 2, because remember u is sine of x, times sine x plus 1. And that would be our factor. Now eventually you got so good you never had to do this substitution. This is what we call U substitution. And basically what U substitution is, you take the part that's most difficult and you replace it with the letter U. The sine x is what's making it complicated, so by replacing it with U, it made it less complicated. Integrating a problem like this one is very similar to this, where we are going to replace the part that's most complex with U. So let's look at an example. This is the ultimate goal of integration by substitution. We want to replace all of the x's with u's. Just like any relationship you've ever been in. If you have been in a past relationship with somebody, you have pictures. If you go with somebody else, you're going to replace them with your new person. So replace all of the x's with u's. If we cannot replace one, we want to make sure that we can eliminate them. So anything we can't replace, we have to eliminate. Sometimes we will call this is sometimes integration by substitution, is sometimes called the reverse chain rule. And you're going to see why we call it that, hopefully in just a few minutes. So let's look at the original problem. So we want to integrate this x squared plus 1 to the fifth to the 2x. When I say reverse chain rule, this is what I'm looking at. I want the derivative of the outside and the derivative of the inside. What I'm looking for is that inside derivative. In other words, one of these products is going to be the derivative of the other. And if you notice, 2x is the derivative of x squared plus 1. So I want to try to notice that 2x is the derivative of x squared plus 1. Therefore, we are going to use what we call U substitution to solve this. Your U will be the inside function. So the U is going to be this x squared plus 1. So when we do U substitution, we're going to let U be the inside function. U is inside. Now, so far, if I were to rewrite this, I would have U to the fifth 2x dx. Well, I still have to replace the 2x and the dx. Well, the dx isn't so hard to replace because the dx is a differential. So all we're really doing there is so if I take the derivative of u, we would get du. Remember, u is now a function of x. Du dx, we're going to use Leibniz, would equal 2x. And just like the differentials, we want to isolate the u. So I would get du equals 2x dx. And this should look familiar to us. This is our differential right there. There's our differential. We solved those the other day. You might remember that. Look at another video. But that doesn't replace the dx. To replace the dx, we would get du over 2x. And this is what we want. Both of these. These are what we're going to use to replace. So my new integral would now become x squared plus 1 to the fifth, but we replace that x squared plus 1 with u to the fifth times dx. I can't replace it. Well, it's 2x, but the dx, I could write that as du over 2x. And if you notice, I replaced all my x's, and the 2x could not be replaced, but it will be eliminated. And that's why we always want to find the derivative, because it'll always cancel out. So what we're left with now is the antiderivative of u to the fifth du. And this I can use. This is just our power rule. We would get u to the sixth over 6 plus c1, your constant of integration. One last step. We have to replace u. Don't forget to replace your u. Just like you did last year in pre-cal, your teacher wouldn't have accepted as u plus 2, u plus 1. You had to replace it. And if I replace my u, well, u is x squared plus 1. We would get x squared plus 1 to the 6th over 6 plus c1. And there's our final answer. Very easy to do. So let's take a look at another one here. Ready? Number 2. I don't like things on the bottom, so I'm going to bring that up. Because there's no quotient rule, I'm going to bring it up to the top. This becomes x times 3x squared plus 2 to the negative 1/2 dx. And I'm looking for a derivative. Okay? Well, if I look here, if I look at the outside is x. The inside is just 3x squared plus 2. The derivative of the inside would be 6x. That's an x on the outside, so I'll go with that. So a quick hint, again, is u is always the inside function. It's always inside of something. So if I let u then be this 3x squared plus 2, now remember that's going to replace this with u. I still have to replace the dx. And I'm going to kind of go here. I'm going to kind of skip a step. If I take the derivative, du, this becomes 6x dx. Now remember, it is really d, like over here, du over dx equals 6x, but we would multiply by dx anyways. I just kind of skipped that step. So dx then would be du over 6x. These are what we want. Okay? And I'm going to rewrite my integral now as, now remember, I'm not replacing my x with anything. So this is x times u to the negative 1/2 du over 6x. And notice what happens. Again, the x's do cancel. Now here's a hint. If you're left with u and x, you have a problem. Okay? Only one variable should ever remain in here. You cannot have u and x in the same integral. We can't integrate those yet. So what I'm left with, now this is a constant. I'm just going to go ahead and factor that out. 1/6, the antiderivative, u to the negative 1/2 du. Notice, No more x's. Everything is now in terms of u. Okay? We don't want any more x's. No more x's. Just like in the relationship. No more x's. But this I can integrate. I'm going to get 1/6. This becomes u, add 1, 3/2. Invert and multiply it, we get 2/3 plus c1. Now I'm going to do two things at once here. One, I am going to oops, that should be a 1/2, positive 1/2. There we go. Whoops, sorry about that. And that should become a positive 2 over 1. Sorry, negative 1/2 plus 1 is 1/2. And you flip it, you just get 2 over 1. So I am going to simplify this to make this 1/3. And again, I am going to replace u. And u, again, in this situation is 3x squared plus 2 to the positive 1/2 plus c1. There we go. And there's our antiderivative. All right, come back to part 2. We'll take a look at how is this magic working for us. And we'll take a look at some more examples. I'll see you then.